Hello everybody and welcome back to Linear Algebra at Frederick Community College. In this video I will discuss diagonalization of matrices, and in particular I will go through two examples where we attempt to diagonalize 3 by 3 matrices. Now in this video the solutions are already worked out, so as you're working through these problems you will need to stop, pause the video, and make sure that you can complete the steps in the solutions. Okay, let's go ahead and take a look at the first example. It says, if possible, diagonalize this 3 by 3 matrix A. And we've done problems like these before. So the first step is to compute the eigenvalues by finding the characteristic polynomial of this matrix. So what do? We set up the determinant of the matrix A minus lambda times the identity. And in this example, I'm using first column expansion. Okay, you can use any method for finding the determinant of a matrix. And we come up with this nice cubic polynomial, negative lambda cubed minus 4 lambda squared minus 4 lambda. It factors nicely. Okay, we get two eigenvalues. One is 0 with the multiplicity of 1, and then the second eigenvalue is negative 2, and that one has multiplicity of 2, and that's because the factor lambda plus 2 appears twice in the characteristic polynomial. Okay, so this is the step where you have to do some tedious computations. Okay, but once you do compute your characteristic polynomial, typically in these problems, they factor out nicely. Okay, what is the next step for computing eigenvectors? Okay, we need to find eigenvectors associated with each eigenvalue. So what do? For the first one, lambda is equal to 0. We set up our augmented matrix A minus 0 times the identity. Okay, we're solving this homogeneous linear system. Now, if you take a look at it carefully, and you'll see what we're really trying to do here is just trying to find the null space, right? Because lambda times 0 times the identity, that's just all zeros. Okay, so once we find the solution to this matrix equation, we're really finding the null space. Okay, which also is an eigenspace. And what does that look like? Okay, so the eigenspace for lambda is equal to 0 is the 0 vector, which is not an eigenvector by itself, right? By definition, that cannot be an eigenvector. Unit with what? The span of this basis element, -1, 3, 1. So that gives us a line in 3 space. Okay, so we have a one-dimensional subspace of R3, and here I'm giving you a visual representation of what that looks like. Okay, we have our vector -1, 3, 1 that generates all of the eigenvectors associated with this eigenvalue. Okay, and what is this eigenspace? It's just a line. It's a one-dimensional subspace of R3. Okay, so that is your first step. Second step is do the same thing for the second eigenvalue. Now, this eigenvalue has multiplicity 2. Okay, we carefully set up our matrix A minus -2 times the identity augmented with the 0 vector. Okay, so I highlighted the numbers in the matrix that are changed. Okay, those are on the main diagonal. Okay, subtract -2 or add +2. Okay, once we solve this system, what are we going to get? Okay, so we have one pivot and then we have 2 free variables, right? Okay, so what does it mean? The solution vector for this system is a linear combination of 2 vectors, -2, 1, 0, 3, 0, 1. Okay, these 2 vectors are linearly independent. Okay, so what does it give us for the eigenspace. The eigenspace associated with this eigenvalue is the zero vector, okay, separately by its own, just to emphasize that that zero vector is not an eigenvector, okay? And we have the span of these two vectors, -2, 1, 0, 3, 0, 1. So what is this? This is a two-dimensional subspace of R3. I'm going to fix this one right here. This is R3. Okay, this is a plane in R3, and we'll see which one it is. Now, before we proceed, my recommendation is to pick a vector from this eigenspace, non-trivial combination of the basis elements. So I picked t is equal to 2 and s is equal to 4 and computed my vector v. So v is the first basis times 2 plus the second basis element times 4, and I get this vector 8, 2, 4, okay? And if I multiply this vector by the matrix that we're working with, I should get a multiple of that vector, and not just any multiple. It is this vector times -2, and you can check this. So this is a good practice for you to connect all the ideas and make sure that the vectors that we're computing are indeed the eigenvectors, okay? So pick your own t, your own s, pick something interesting, you know, not just like 1 and 1, okay? Pick something maybe with negative values, even a fraction, okay? Use your calculator to see if it works out, okay? So what is the eigenspace? What does that look like? Here I'm giving you a graphical representation of the eigenspace associated with this eigenvalue. It is a plane that's spanned by these two vectors, okay? So -2, 1, 0. It's easy to grab these two vectors. The other one is 3, 0, 1. So it's a plane that goes through the origin and it's generated by these two vectors, okay? And everything except the zero vector is an eigenvector, right? So the zero vector is not an eigenvector, but we need to have the zero vector to have a vector space, okay? So these two subspaces, okay, they contain all possible eigenvectors, all right? So the one line up here and this plane right here, they contain every possible eigenvector of this matrix, all right? So we have 3 linearly independent eigenvectors. That's good, that's what we want, okay? We construct our factorization now. What is our D? D is the diagonal matrix that contains the eigenvalues on its main diagonal, okay? So I have 0, -2, and -2. Then the matrix P is the one that contains linearly independent eigenvectors. And let me make sure that everything lines up correctly. So the first one, the first vector here is associated with the 0 eigenvalue. The second one is -2, and the same one for the third one. And look, we have multiplicity of -2 is 2. So it makes sense that we have this repeated value, right? Okay. So now, what about P inverse? That just you can compute on a calculator. And it's a good idea to check if this works out. It's not difficult to plug this into your calculator, so I'm going to go ahead and do it. Okay, and I already saved my matrices. So what are my matrices? I'm using D, that's the matrix that contains my eigenvectors. And then I also have my diagonal matrix, E. And then I can just do D inverse, okay? And we get exactly the matrix that we started with, okay? You can check that that's what it is. So this is a good idea to check your work with a calculator. Make sure all of the entries are the same, okay? So that's your first example We've done several of problems of this type by now, okay? So the most tedious computation usually happens on the very first step where you need to find the characteristic polynomial, all right? Now, let's take a look at the next example. This one says, if possible, diagonalize the matrix B, okay? Again, we're working with a 3 by 3 matrix. We need to find the determinant of B minus lambda times the identity, okay? So I set up my matrix, I compute the characteristic polynomial, and I get the following. I have negative lambda plus 2 squared times lambda minus 2. So once again, I have two eigenvalues. Lambda 1 is equal to 2. That one has multiplicity of 1. Okay, we only have one factor of lambda minus 2. The second eigenvalue has multiplicity of 2. We proceed just like we've done before. Okay, start looking at eigenspaces. So for the first eigenvalue, okay, the one with multiplicity 1, we compute our eigenvector, okay, by again row reducing this matrix B minus 2 times the identity. We get a nice solution in this case, okay, we have one vector, and that makes sense. Negative 1, negative 2/3, 1, those are the coordinates of your basis eigenvector that generates the entire eigenspace, okay? So this is a one-dimensional subspace of R3. Again, that's another line that goes through the origin, okay? So no questions here. Now, once we start working with the second eigenvalue, okay, so that's the one that has multiplicity 2, what happens in this scenario is the following, okay? So you set up your matrix B minus negative 2 times the identity, you row reduce it, and in this case, we get 2 pivots and only one free variable. That gives us what? That gives us one eigenvector. Okay, so your solution vector is of the form negative 1, 0, 1, okay, times some parameter t. That gives us what for eigenspace? That only gives us a one-dimensional subspace of R3. So your eigenspace associated with negative 2 is just the 0 vector, okay, union with a span of negative 1, 0, 1. So again, this is a line in 3 space that goes through the origin, okay? But we have multiplicity 2 over here, okay? That does not match up. It doesn't mean that we've done something wrong. It just means that there is no eigenvectors. There's not enough eigenvectors to generate a basis. Okay, so if we list all of our eigenvectors, there's only going to be 2 linearly independent. Which ones are they? Okay, the linearly independent eigenvectors are negative 1, negative 2/3, 1. Okay, and then the other one is negative 1, 0, 1. That means we cannot have a basis for R3 that's built just out of the eigenvectors, okay? There's not enough of them. So B is not diagonalizable, okay? There is no way for us to construct that matrix P, okay? There's nothing wrong with the matrix, that's just what that means, all right? So if you were to look for a non-standard basis for R3, for this particular matrix, we cannot make that basis out of eigenvectors, all right? So this is where you would stop. You would say, no, B is not diagonalizable, okay? All right, so as you can see, the steps are exactly the same. And there's no way to just say it one way or another by looking at the matrix. We have to do all these steps. We have to find the characteristic polynomial. We have to compute eigenvectors associated with each eigenvalues. And then the ones we need to kind of keep an eye on are the ones where we have multiplicity not 1, right? So multiplicity greater than 1. If you have multiplicity 2, 3, and so forth, depending on the size of the matrix that we're working with, then we want to make sure that once we compute eigenvalues, eigenvectors, we have the same number. That is, the same number as the multiplicity. That is, if we want this matrix to be diagonalizable, right? That doesn't happen all the time. In this case, we did not get enough vectors to generate the eigenvector basis. Okay? All right, so 2 examples we worked through. Make sure that you know how to do all the steps. Make sure you know how to come up with examples of eigenvectors from all of the eigenspaces, and then come up with the correct conclusion. All right, thank you for watching.